everyone. Today we're going to be discussing this question, which I originally found in the Griffith's Electrodynamics textbook. And it goes into a little bit of detail about how to solve this question, but I thought it would be nice to have a step-by-step walkthrough of how this question might be done. So the question goes, find the magnetic field at a distance z above the center of a circular loop of radius r, which carries a steady current I. Now that is a lot of words, so let me draw out what they mean by all this. Okay, so first we have a circular loop of radius r, and above this loop is some point P, and this loop has a current going through it. Let's just say it's in this direction, and this current is called I. And this is what it gives us. Oh, it also gives us that the height from here to here is z, and that's what it gives us. So how do we approach this problem? First, we need to think about what equation it is that tells us the magnetic field from a current carrying wire. And then we can extrapolate from that. And that equation is the biot-savart law. And it goes like this in its differential form. It says dB is equal to mu naught I over 4 pi times dl cross r hat over the magnitude of r squared. Now, that's a lot of symbols, some of which I have yet to define, so let's go ahead and define these. dl is the differential length element of this wire. So for example, the differential length element here looks a little bit like this, and we call that dl, and because it's a vector it actually has a direction, and we're going to say that the direction is in the same direction as the current. Okay, so that's dl, and then we have r, and r is the vector that points from dl to the point P, to the point of interest. So switching to maybe yellow or blue. Blue's nice. It's this vector here that points from dl to the point P. We call that r. Now, that's a lot of stuff. And let me actually drag this down a little bit here. So, what do we know about this value here, dl cross r? We know that it's a vector. And we also know, because it's the cross product, we also know that it's going to be perpendicular to both dl and r. So in other words, it's going to come out like this, very nearly, at a right angle. Okay? And it comes out at a right angle, but it could have been this way, or it could have been this way. But the reason I knew it was in this direction is because of the right-hand rule. I can't show you my hand right now, but if you did dl and you crossed r, your finger, your thumb, would be pointing in the direction of that yellow arrow right there. Now, that's all fine and good, but something that we have to consider is the fact that this is only the differential magnetic field element. We have to take the sum of all of the dl cross r's. So the dl right here, and then the r that goes from that point, from that dl to the point P, the dl right here, the dl right here, the dl right here. Every infinitesimal dl we have to take into consideration. Now that may seem like a hassle, but it's actually quite nice because this is a symmetric problem. So the dl that we have shown here, part of it will be canceled out by the dl here. So we have another dl vector there. It's going in this direction, and r points to the point P, which means that the dB in this direction is going to point this way, still at a right angle. Now, if you take that into consideration for every single point along this line, along this circular wire, we find that this makes a cone, a cone of magnetic field, or of magnetic field vectors. And that the horizontal components of these will all cancel out. So this leftward component will cancel out this rightward component. This leftward component will cancel out this rightward component. So all you're left with is the two vertical components of these two vectors added together. Okay, let me clear off some of this clutter that I have. So what does that mean? That means that all we really have to worry about is the vertical component of each one. We just have to add together the vertical component of each of these vectors, which is nice because now we don't have to worry about direction. We can just worry about magnitude, and we already know the direction. We already know it's in the z-hat direction. So how do we find that, though? How do we find that vertical component? Well, as we do in many cases when we have to find a component, we need to think about it in terms of angles. Now, we're going to define this angle here between, let's say, here's another radius here. That's another r. I'll erase this one to remove the clutter. We're going to call the angle between little r and big R, we're going to call that theta. Now, the nice thing about theta is that it is also this angle. Now, I will prove that to you in another video. It takes a little bit of time, and I don't want to take up too much of your time, but for now, just take my word that this angle between the vertical and dB is also theta. Now, this makes our problem very easy, because in order to take the vertical component, we just note that dB here is the hypotenuse of a triangle, and this vertical component is the adjacent side to theta. So all we have to do to take the vertical component is multiply dB by cosine theta. And now we just have the vertical component. So now we can think that the differential of our magnetic field is actually dB cosine theta, which corresponds to this this rather large thing here. Excuse me. This thing here. So if we take the sum over all of these terms, it will give us our full magnetic field. So what do we call it? A sum over a whole bunch of things, an infinite number of things? We call that an integral. So we need to change this to integral form. But the last thing we need to do before we can do that, is sort of make sense a little bit more of dl cross r. We already know, in a way, what direction it's going in, but we should also think about the magnitude of that vector. So what we need to go to, I'll circle this again and bring it over here. We also need to think of the definition of cross product. So if you recall, A cross B, where A and B are vectors, is equal to the magnitude of A cross B, rather, is equal to the magnitude of A times the magnitude of B times the sine of the angle between them. Now, I don't want to use theta because we have a different theta here, so I'll call it phi. That's the angle between the two vectors. Now, what is the angle, rather, between dl and r? Because really what we're working on here is dl cross r. So this is going to be the magnitude of dl times the magnitude of r hat. Sorry, it's r hat. Times the sine of the angle between them. Now, what is the sine of the angle between them? Let's look at this. So we have one arrow going this way and one coming off into space like this. It's a little hard to tell, but in fact the two vectors are perpendicular to one another. And this might help visualize that. Yeah. So they are, even though they're not in the plane that we're looking in, they are 90 degrees from one another. And that makes this really easy, because this just becomes sine of 90. So then dl cross r hat, sine of 90 is 1. Magnitude of r hat is also 1. That is the definition of a unit vector. So this is 1, this is 1, and so all we're left with is the magnitude of dl, which we're just going to call dl without the vector symbol over it. So this really narrows things down for us. It really helps us out. We're going to write db out in using all the substitutions that we've just found out. So b now, right, because we're taking the integral over all of the db's, right? B now is equal to, take out all the constants, 4 pi. Let's see, r squared here, the magnitude of r squared is always going to be a constant for any given point P. So we can take that out, just call it r squared. Excuse me. R squared. And even because r is constant, the cosine of theta is also always going to be constant, because theta is always constant, times the integral of, well, all that's left now is dl, because we already found out that dl cross r here, dl cross r here, is just equivalent to the magnitude of dl. Okay? So all we have here is dl. Now, what do we call the integral of dl? The sum of all of these little length elements? Well, that's just the circumference of a circle. So that's going to be 2 pi r. Fantastic. Now, cosine of theta, we have to be careful because theta is something that we used. It's a tool that we came up with in order to make this problem a little easier. We want to get it back in terms of things that are given in the problem. Well, that's pretty easy. We can think about cosine of theta as right, it's opposite over hypotenuse, right? Sorry, adjacent over hypotenuse. Wow, I gotta brush up on my trigonometry. And the adjacent in this case is just big R, the radius of the circle, and the hypotenuse is r hat, or r vector. Now, what is the... R vector is also a tool that we made up. So what is r vector equal to? Well, it's just equal to the square root, using the Pythagorean theorem, it's equal to the square root of r squared plus z squared. So that's what cosine of theta is equal to. So we can replace this with r over square root of r squared plus z squared. That's a big R. Okay. Wow, that's a lot of stuff. So I hope this is all clear to you, because I'm going to delete some of this and move my work over here. Goodbye, work. Okay, cool. I am going to rewrite my work over here. So, replacing all of these things that I have over here, we have that B. I can already tell that I'm not going to have enough room. We have that B is equal to mu naught I over, we're going to keep things in terms of little r until we absolutely have to change them back. R squared times r over big R over little r. These are all the magnitudes, just as a reminder. Times 2 pi big R. Well, we can just cancel some things out here. Cancel out pi and pi, change that 4 into a 2, combine these r's, combine these little r's, and we are left with B equaling mu naught I over little r cubed times 2 times r squared. And now in terms of everything, only things that we had from the original equation, we have B is equal to mu naught I over mu naught I r squared over 2 times the square root, actually, let's write it like this, times z squared plus big R squared to the 3/2 power, because R itself is this term to the 1/2 power, and so when you cube it here, this is to the 1/2 power, and when you cube something to the 1/2 power, you get something to the 3/2 power. So this then is very nearly our final answer, and you may have noticed I've been forgetting something this whole time. I've been putting this arrow on this, I've been putting this arrow on this vector, or on this B, when I haven't been treating this system, or this equation, as a vector. So the last thing that's missing is this is all in the z hat direction, which is something that we concluded at the very beginning. All right. That's it. This is this was a very long process, so feel free to go back and play this at half speed or twice speed if you want, um, and uh, and follow through with me. And I think you'll find that although it's a lot of work, you've learned a lot of skills in order to find magnetic fields from all sorts of shapes of wires. Maybe a square of current going through a wire, or even an oval, which would be a little bit harder, but I think you could do it now that we've done this. And again, this was made a lot easier by the fact that we had symmetry in the original problem. If you try to do this even a little bit off axis, it will get significantly harder. But for now, for all of all those of you who are wondering, this is the magnetic field from a circle of current carrying wire, if you're measuring right on the axis. All right, thanks. And remember to like and comment if you have questions or additions to what's been said here. It all really helps. Thanks.